Video, I'm going to talk about magnetic levitation, what that means, and some strategies, or a strategy for how you can do it. So first of all, what is magnetic levitation? So magnetic levitation is levitating an object in space. So keeping something from touching the ground down here via magnetic forces and fields. So in this video, we're going to talk about levitating a permanent magnet, which is like what you would have as a kid, one of these U-shaped devices, and it would draw in from around it other objects that move toward it. So this representation of magnetism can be thought of as fields. So coming out of this permanent magnet here, we have magnetic fields. They can be abstracted to lines with a direction going from the north end to south, which is a concept you're probably familiar with. So to levitate this magnet, what we're going to do is use another magnet that will be mounted above. So this magnet will also have magnetic field lines, and they will be large enough that they will interact with this other magnet and bring it upwards using simple magnetic attraction, like in these magnets. So to do that, we made a solenoid electromagnet, which is basically a coil of wires all around a center. So it makes a big cylinder like a spool of thread, and we chose as our center to use an iron core. So there's an iron rod in the middle that we wound a bunch of wire around, and so to get the magnetism of this device, you can use something called Biot-Savart law, which states that the magnetic field, which we'll call B, is equal to mu sub k, which is a constant that is determined by the core, so in this case steel, times mu naught, which is the permeability of free space for magnets, and that all over 2 pi times the integral of I dl cross r over the absolute value of r cubed is equal to magnetism. So we've got some stuff in here, integral. Basically the important pieces to pull out are that the magnetism is proportional to the current that you put in, this I, that it falls off essentially as 1 over r squared. So as you move away, the magnetic interaction gets smaller. And specifically for us, it's important to know that there is a mu k term, which means that we can amplify the magnetism using the core. So mu k of an iron substance can be as much as 1,000, 2,000. It can be really big, so it's a large factor. And so into our solenoid, we're going to put current, an I, and that is going to create those magnetic fields we talked about before. And depending upon the strength of this field, which is determined by the I we put in, which we can change because we're building the circuit that powers this, we can affect how strongly this magnet here, this permanent magnet from before, is going to be pulled upward via the force of magnetism, which will be resisting the force of gravity. So when Fm equals Fg, based upon Newton's second law that F equals ma, we'll have A equal to 0, which means that it will not accelerate upward or downward, and assuming it has zero velocity at that point, it won't move, and it will levitate in space. So to do this, there is a challenge, which is that if we start the magnet at rest down at the bottom, say on this floor with the solenoid above it, it starts with a force of gravity, and if we increase the strength of the field from the solenoid, this green strength, or this green field, I guess, if we increase this until it interacts with this permanent magnet and makes the force of gravity equal, or the force of magnetism upward equal to the force of gravity, like I said before, and then we go past that, so Fm is greater than Fg, and we accelerate upward, it means that our magnet is going to move up, and the field Fm is going to increase because we're getting closer to the magnet, which means that 1 over r squared term is getting greater because the r squared is getting smaller and it's in the denominator. So we're going to end up with this magnet here, and our field lines coming out of each of them. And if we don't change the field of our solenoid, we're going to have a case where Fm is much greater than Fg, and it's going to stick to the solenoid. So we're going to have this case we don't want, where they're physically in contact, where it will be levitating, but it will be levitating against the ceiling rather than in space, which is not what we want. So there's a way we can get around this, and that is called a controller. So we can build something that makes sure that our magnet does not get pulled into the solenoid that we built. And so the way we're going to do that is to modulate the current through our solenoid, so this input current here, and there is an abstraction of that, this controller. So the first step is to measure something, and in this case we're going to use Hall effect sensors to measure the magnetism on top of the solenoid and on the bottom of the solenoid. So this measures the strength of those fields that I've been drawing, and so if we subtract them from each other, we should get 0, because the strength on the top and bottom of the solenoid right in contact with it will be the same. So B top minus B bottom will equal 0, unless we have our permanent magnet there with its own field, and then B top minus B bottom will be proportional to the height of the magnet. So we're going to use this height of the magnet as what we're measuring, and we're going to have a set point somewhere within here, a given voltage that is resulting from the magnet being in that position, and that will be output by our Hall effect sensors. And so that's going to be input as our set point, and it's going to go into a controller. And so our options generally for feedback controller are PI and D, proportional, integral, derivative. So we're not going to use derivative, we're going to use proportional and integral. And so we're going to scale those by some factor Kp and Ki, which are going to determine how strong each of these interactions is in controlling our magnet. And so instead of having our magnet move from the ground all the way to the top and make contact, we'll instead hopefully have our magnet move from the ground up and then back down as the current drops, and then back up and down and up and down until it stays at a constant level, which will be our set point, or it will be measured by our Hall effect sensors and result in a value of our set point.